The next problem that we will do, known as the rotating rod viscometer problem, or the flow caused by a rotating rod partially submerged in a large liquid reservoir. And the setup is as follows. You have this kind of large pool of liquid, and you put in a rod, and that rod is of radius r, and you start spinning the rod at a constant speed omega, and there's air over here, and there's a liquid here, and as you spin the rod, depending on the speed, what we observe experimentally is something kind of like this surface. Okay, surface is going to do something like this. Okay, I'm exaggerating the drawing over here. Okay, so how do we do this? Well, the first step is we're going to assume that this is a steady state flow, constant properties, etc. And we've already visualized the flow. Now from a top view, what this looks like, you're going to see the rod in the middle over here spinning at a constant speed omega. Then you're going to see kind of the streamlines centered at the rod, and they change with the distance from the rod. Okay, and these are the only velocity component is the tangential velocity components. So it makes sense to go ahead and do cylindrical coordinates, obviously. And so we're going to do r and theta and z. Okay, we're going to put our coordinate origin at the bottom of the cylinder. Step 3 now is we're going to look at some of the assumptions. So we are going to assume that UR and UZ are equal to 0. UR equal, UZ equal to 0. So there's no flow in the vertical direction. There's no flow in the radial direction. The only flow is tangential. The only velocity component, U theta, is not equal to 0. Now, in terms of gradients, du theta by d theta is equal to 0. We're going to assume that the velocity is probably going to be constant along each of these circles. It will change as a function of r. So du theta by dr is not 0, but it's 0 in the z direction. Okay, du theta, same velocity at different z planes, and same velocity at different thetas for the z direction. Okay, obviously the other guys, all their gradients are 0. For the pressure, dp by d theta is 0, but dp by dz is not 0. Hydrostatic, just by virtue of the weight of the liquid. And dp by dr is definitely not 0, because that's the centripetal force that is pushing the particles, the fluid particles out, okay, as we spin. Okay, so that gives us some of our basic assumptions. Okay, so now we can write the governing equations. We're gonna do the r and theta and z components of momentum. And for the r component, I'm gonna start by using this space over here. R momentum. We have rho dur by dt plus ur dur by dr plus u theta over r dur by d theta plus uz dur by dz minus u theta squared over r is equal to minus dp by dr plus let's write this down, plus mu into d by dr of 1 over r dur by d dr dur by dr plus 1 over r squared d2 ur by d theta squared plus d2 ur by dz squared minus 2 over r squared du theta by d theta, and that's there's a I think there's a mistake over here, okay, plus rho g r, okay, plus rho g r. Okay, so now we can start canceling terms. I mean, we could have anticipated what terms remain in this equation, and obviously we're going to have the dp by dr and the rho u theta squared over r. But anyway, so dur by dt steady state, this guy is 0, this guy is 0, and this guy is 0. So is this guy is 0, this guy is 0, this guy is 0, this guy is 0, and we are left with minus rho u theta squared over r equal minus dp by dr, or dp by dr is equal to rho u theta squared over r. So this will actually give us the key relation between the pressure and u theta. Now, the question here is to find the shape of the interface. And the way we're going to do that is we're going to find the pressure distribution and say at the interface the pressure is equal to the atmospheric pressure, and that essentially gives us a way to solve for the height, because the pressure distribution is going to be is going to have terms that include the height from the bottom, so the height all the way to this surface, and that's how we're going to solve for this. For the theta momentum equation, again, you can write down the entire momentum equation in the theta direction. All terms disappear except for the diffusion term, or for the stress term. So that gives us d by dr into 1 over r d by dr r u theta. That's equal to 0 because there's all other terms just disappear. This will give us the form of u theta. Okay, and finally for z momentum, same thing happens. Everything disappears except for the hydrostatic pressure distribution, and that gives us dp by dz, so minus dp by dz minus rho g, so that gives us dp by dz equal minus rho g. Okay, so now we have all three governing equations, and note that the continuity equation doesn't give us anything. If you apply continuity, if you apply the continuity equation, you get 1 over r d by dr r ur plus 1 over r du theta by d theta plus duz by dz equals 0. And indeed, each one of those terms, so this guy is 0, this guy is 0, and this guy is 0, so all you get is 0 equals 0. Nothing. Doesn't help us much, except just validate our assumption. Okay. Now, in terms of boundary conditions, let me write this in red. So for boundary conditions, u theta at r equal r at the surface of the rod is equal to r times omega. Remember, omega is like radians per second, so you need to multiply by a dimension, which is the radius. That gives you the radial, the tangential or radial velocity at the surface of the cylinder. And another interesting addition is that u theta at infinity should be equal to 0, because this is a very large fluid. We call this the far field condition. Okay. Next, we can start integrating the equations. Okay, so we said that the theta momentum equation is going to give us the form of the velocity. Okay, so that gives us a u. So let's remember what that equation was d by dr of 1 over r d by dr r u theta. So 1 over, so d by dr of 1 over r of d by dr of r u theta is equal to 0. So a first integration gives us 1 over r d by dr of r u theta is equal to a constant. Okay, in other words, d by dr of r u theta is equal to c1 over r. Then we can do one more integration. C1 r. We can do one more integration that gives us r u theta is equal to c1 r squared. If you want, c1 over 2 r squared plus c2. So this implies that u theta is equal to c1 over 2 r, okay, plus c2 over r. Okay, we divided by r over here. Okay, so now we looking at the boundary conditions, BCs. At infinity, u theta at infinity is equal to 0. Just by virtue of this condition, this guy is going to blow up. So we have to get rid of this term. So this implies that C1 equal to 0. There's no C1 in the first place. So u theta is simply C2 over R. Now, u theta at the surface of the rod is equal to R omega. And that's equal to C2 over capital R. So this implies that C2 is R squared times omega. And finally, we substitute. This gives us u theta is equal to R squared omega over R. Okay, so that's u theta of R. Okay, so that's only a function of R. Okay, so now we need to calculate the pressure distribution. So if we go back to these equations, we are left with these two terms. We can put in u theta over here and start by integrating. So let's go ahead and do that. So for the R momentum equation, R momentum, that's going to give us dp by dr is equal to rho u theta squared over R. So that's dp by dr is equal to rho u theta squared by over R. Okay, rho u theta squared over R. And that's equal to rho R squared omega over R squared. Agreed? So that's rho u theta squared. So that gives us rho R squared. We have a u theta squared. Sorry. So we have so this becomes R to the 4 omega squared R squared. So this becomes R to the 4 omega squared R cubed, right? So u theta squared is R to the 4th omega squared R squared over R. So that gives us an R cubed. So this completes the dp by dr. And if we integrate once, this gives us P equal to rho. So this is an integration with respect to R. So that gives us a rho R to the 4th omega squared over R2 R squared. Okay, so minus, over minus R to the 4 omega squared over 2 R squared plus some function of Z, because that's the only remaining component. Now we're going to take this pressure and put it in the equation, in the last equation. But Z momentum tells us, implies that dp by dz is equal to minus rho g. Minus rho g. So we differentiate this guy, we get 0 plus df by dz is equal to minus rho g. So this implies that f is equal to minus rho gz plus some constant. Let's call this k. Okay, so now this is f of z. Okay, and that relates to the that puts everything in the pressure. So finally, this completes the solution for the pressure. As P is equal to minus rho r to the fourth omega squared over 2 r squared minus rho gz plus k. We still need to find k. Okay. All right, so how do we find k? We're going to take the same fluid. So we're going to take the rod, and that's immersed in the fluid. And you know, at the at the end, we have kind of something that looks like this. Okay, something that looks like this. So remember now, as this interface moves, this is going to be air. Okay, so we're going to call this distance over here h, which at steady state, this h is going to be constant. So we're going to say that, and the pressure over here is going to be P atmospheric, or P0. Okay, so we're going to say that P at RH is equal to P0. That's the atmospheric pressure. And then we substitute, we take our formula from previous, which is P at RH, that's minus rho r to the fourth omega squared over 2 capital R squared minus rho GH plus K equal to P0, correct? And that should allow us to obtain K. In other words, K will be equal to P0 plus rho GH plus rho r squared omega squared over 2, and therefore P is equal to minus rho r to the fourth omega squared over 2 r squared, right, minus rho gz plus k plus P0 plus rho gh plus rho r squared omega squared over 2. So let's collect some terms. We're gonna put P minus P0 on the left hand side, and over here we're gonna take rho r squared omega squared over 2 into 1 minus r squared over lowercase r squared plus rho g h minus z. And that gives us the pressure distribution in the fluid. Now we say at the interface, z is equal to z 0, okay, and p is equal to p0. So therefore p minus p0 is equal to 0, and then we plug this in here, so we get rho r squared omega squared over 2 into 1 minus r squared over lowercase r squared plus rho g h minus z0 is equal to 0. And that gives you the shape. So this is the shape, C0. That gives you h, or C0 minus h. So I'm going to take everything to the right-hand side and multiply by a minus sign. So we get r squared omega squared over 2g, because rho and rho cancel out. We divide by g to 1 minus r squared over r squared. And that is how we obtain this.